So if you're just joining, hello, I'm Jeff Squyres. I'm from Cisco. This is going to be a deep dive into so Cisco's hardware, our NIC, our OS bypass technology, how it works, and then how we use it inside Open MPI. All right, first thing, most of you might not realize we actually sell servers now. I have to apologize right off the bat. The marketing guys maybe put a couple slides in the beginning. But we sell servers now. We've been selling them for about 4 years. It's actually going remarkably well. We sell, we have a whole variety of, they're x86 servers. They're all Intel based. We don't do any AMD. But we have, our product line is called Cisco UCS. It stands for Unified Compute System. We actually sell NICs now too. We've never sold, so this is, most people, this blows their mind. As a giant networking company, we have never sold a NIC before. We always sold switches and routers and things surrounding it, but we never actually sold NICs. Now that we sell servers, we actually sell NICs. And I'm going to talk a lot about this particular NIC. And then, of course, we have a huge range of switches that we do. The cool thing about it is that our servers, for being the new guy in the business, we actually have set a pile of records for serial performance. And yes, this is about parallel computing, and so that really doesn't matter as much. But to get good parallel computing, you got to start with good serial performance too. So it's actually pretty important, the work that my serial compadres at Cisco have done as well. And we've got this whole ultra low latency Ethernet. And I know it's hard for a lot of people to believe because most people associate Ethernet. Oh, that's the slow thing, right? Well, no, actually it's not. It's just no one's ever done a good OS bypass on Ethernet before. And so I'm going to talk about what a good one is, in my humble opinion. And then we have awesome 40 gig top of rack cores and switches. All right, so again, we have a bunch of different models. I'm not going to go into this, but I have to be able to say that I showed it to you. So we have, you know, rack servers and blade servers, and we even have ones that do giant memory. So I think this model here can get 1.5 terabytes of RAM in it for like really, really big RAM jobs, which is actually just pretty cool. All this stuff is Ivy Bridge, as you would expect. It rocks. You should buy it. And this one is, I did not make this slide, right? But what's really cool is that, so the green line is Cisco. This is worldwide blade sales. We sell more blades than Dell and IBM. The undisputed king for now is HP, so we are nowhere near that. But I mean, look at our line is going up and to the right, where all the others are losing market share. So in 4 years, that's pretty cool, right? I'm not a markety kind of guy, but that's pretty cool. All right, and lots of records. We have set lots of records according to all the spec benchmarks, blah, blah, blah. I think all details, if you really care, all the details of this stuff, you can find it on cisco.com. Okay, so one of our value propositions, particularly when you start talking about 40 gigabit Ethernet, is if you think about a lot of HPC clusters today, you have a TCP-based network for your SSH and your NFS and your commodity traffic, and then you have an MPI network. Well, that seems like kind of a pain, right? Why do you have to manage 2 different networks? Why don't you just have one big honking Ethernet network that can handle everything? Now, again, that's not necessarily appropriate for everybody, but this now becomes a possibility if that's good for you, right? So you can actually have real quality of service. And you can say, oh, well, I'll dedicate this fraction of it for, you know, SSH interactive traffic, this much for file server traffic, and the rest of it for MPI, or whatever, right? And again, not necessarily suitable for everybody, but it is actually a very interesting use case for a lot of people. 10 gig is what is today. 40 gig is coming. I'm not allowed to give a date because I gave a date about a month ago and then it slipped and then I got in trouble for saying that date publicly. But let's just say it is very, very, very soon. All right, 40 gig servers exist. 40 gig to the host is coming incredibly soon. These are our lowest latency switches, right? So the Nexus 3548 does 190 nanoseconds port-to-port latency. And so that's actually pretty good. That is both a 10 and a 40 gig switch. This is a 10 and 40 gig switch. Has slightly higher latency. I think it's on the order of a micro port-to-port latency. But it can go significantly higher density. So this might be your core switch, for example. These might be your leaf switches and things like that. You go up to 96 40 gig ports or 384 10 gig ports. All right. And the cool thing about Cisco is that we have a very diverse switching line. I mean, this is what we've been doing for forever. So rather than having just 2 switches that you can choose from to build your topology, we have a lot of different switches for whatever your requirements are. Perhaps you're sensitive on latency. Perhaps you're sensitive on bisectional bandwidth. Perhaps you're sensitive on price. Perhaps you're sensitive on a million other things, right? These are just a couple of different configurations that we do for, you know, a 2-tier spine and leaf, right? Depending on, you know, how many you want, what kind of latency you want, what kind of scale you want, and so on. Many, many, many more are possible. And then you can go even deeper, right? If you want a really large scale out cluster, we know that Ethernet scales, right? It powers the world. So you can do a variety of different things, and we have a whole switching line to let you do whatever it is that you want to do. Okay, enough of the markety stuff. Let's get into the good stuff. Yes, sir. Oh, you're going to make us go more markety. That's fine, as long as it wasn't my fault. Okay. Yes. You had to ask that. So the question is, old classic Ethernet, you can't build a topology like this without spanning tree and all kinds of other awful things. There are newer Ethernet stuff, and I am going to completely forget the name of it. You going to know what it is? Yeah, there's new multi-pathing Ethernet. Yes, that stuff. Data center bridging and Trill, and there's even another name I don't remember, but this is all possible these days with 10 gig and 40 gig Ethernet and so on. So great question though. Okay, let's get into the good stuff here. Userspace NIC. All right, so here's our NIC. This is one of the PCI form factors of it. That is, we call it Userspace NIC for the. It's no surprise to HPC people. It is direct access to the hardware from Userspace, right? So it's OS bypass stuff. Right, and we did it with Linux verbs because that is what is upstream, not because it's a great API. But it uses what we call, we didn't want to call it a NIC because why call it a NIC, what the rest of the world calls? We call it a VIC, a virtual interface card. And actually there's a reason for calling it a VIC because this does SRIOV, which I'll talk about in a few minutes, which can make itself appear on the PCI bus up to 256 times. And that's really good for virtualization kinds of things and doing hypervisor bypass kinds of stuff. Turns out, though, that a lot of that technology is almost the same thing as what you need for operating system bypass and HPC kinds of things. So we're using this well-established technology. This NIC is like 1.5 years old, right? So this is not a new NIC that we invented for HPC. We're using a well-proven NIC, and we did basically a firmware upgrade to it to allow it to do MPI in an ultra-low latency kind of way. Now, other cool things about this, underneath this big honking heatsink here, is an ASIC that we created. This is not a Broadcom ASIC or anybody else's ASIC. This is a Cisco ASIC. It is a 80 gigabits ASIC. This particular form factor has, I think these are SFP plus ports. So this is 2 times 10 gig. But you can imagine what is coming very, very soon is 2 times 40 gig. And again, I gave a date when I presented this in Madrid, and then it slipped and I got in trouble for giving that date publicly, but it's coming really, really, really soon. It has PCI form factors, mezzanine form factors to fit in the blade servers, all these kinds of things. So this is a really cool card. I'm going to talk about it in a bit here. Now, let's get right down to the brass tacks. What are our latencies? So if we do back-to-back raw latency, so when I say raw, I'm not talking verbs. I'm talking basically, it is a user space program, but just strip out all forms of overhead, do completely unsafe kinds of things. No, that's not true. It is safe, actually, but at 1.57 micro, okay? And that's kind of like a ping pong half round trip latency number, all right? And that's back-to-back, no switch or anything like that. And if you put MPI on top of that, so back-to-back, and that's with all the MPI semantics and everything, 1.85 micro. And then if you do that through our lowest latency switch, that is another 190 nano, and you are up to 205 micro. Okay, and so we're actually pretty pleased with this. And the numbers that I presented about a month ago in Madrid were slightly higher than this. So we actually, in the lab, are getting these numbers down farther and farther. So we're actually very, very pleased with these numbers. All right, so just for comparison, and I think most people, this is not any new information, but just to level set us and put us all on the same sheet of music here. On a traditional TCP stack, you know, you are going through an application which goes through the sockets library. You trap down to the kernel into the TCP stack, into the general Ethernet driver, you know, the VIC driver, and then out to the hardware. Or pick your favorite hardware if it's not the VIC, right? But the whole point of an OS bypass is that, you know, you have, particularly in the verbs case, right, you do some bootstrapping by trapping down into the kernel and so on. So at the beginning of time, you set up your queue pairs, set up your protection domains, excuse me, all these kinds of things. But then when you actually go to do MPI send and receive, the fast path completely bypasses, and you're talking straight to the hardware. The hardware has been exposed up into user space, and we can talk straight through that, and you just cut out tremendous amounts of latency that way. Again, this is not new. Just wanted to level set us on the terminology here. All right. So what we do is basically we're directly injecting and slurping off L2 frames from Ethernet. Right. So no TCP, no IP, no nothing. As a matter of fact, you don't even care what it is. It's just we are, you know, directly reading and writing L2 frames on Ethernet from user space. All right. So let's talk about how this is architected a bit here. So the VIC uses SRIOV, and SRIOV, I have another slide on this, and basically all of our queue pairs are manifested inside that technology. So queue pairs is a verbs technology. Do people know what I'm talking about when I say queue pairs? No, all right, I'm sorry, let me take a step back there. A queue pair is a pair of queues, one queue for sending, one queue for receiving. So when I do a send, see a downward arrow from here, goes into a queue pair, which then ends up going out and creating L2 frames and directly injecting that onto the wire. Right? Inbound frames come into a portion of the VIC that we call the classifier, very, very imaginative name, that when frames meet a specific pattern, they are not given to the operating system, they are diverted over into the receive queues, and it picks out exactly which receive queue, which then has been given to the target MPI process. Okay, so there's basically, you know, as a frame comes in, it's got, for lack of a longer explanation, a special pattern in there that says, oh, this is a usNIC frame. This is not, you know, a TCP frame that I need to give to the OS. And in there will be a number that identifies which queue it needs to go into, goes into that queue, and goes straight up to the process. Now, something that plays a big part of this, and I have a couple slides showing this later, is the x86 chipset IOMMU. The IOMMU is the IO, I am blanking on what MMU stands for. Paul? That's the one, memory mapping unit, memory management unit, memory management unit. So it does the mapping between physical and virtual memory, because user space deals with virtual memory, but kernel space and hardware deals with physical memory. So inside the Intel chips these days, they have this IOMMU that we just use to do all the mapping from physical to virtual. All right, I'll talk about that in a little more detail here. All right. So let's talk about SRIOV. SRIOV is a technology that is a standard. This is not something that Cisco invented. We are playing well with others here. Single root IO virtualization. It was invented for, among other reasons, virtualization. It has two main concepts. Well, no, among many concepts, it has two concepts. One called physical function, or PF, and a virtual function, a VF. And typically the way that this is used is that you can have I'm going to take a few shortcuts in my explanation here. We basically associate a MAC address with a physical function. And we can have up to 256 physical functions. And this basically makes it look like there are 256 NICs on the PCI bus. That's what this is used for, right? So we kind of, I'm not going to say trick, but we make it look like there are as many NICs as there are physical functions. And in an HPC setup, the way that we advise using it is that you have one physical function per physical port, right? So you're not actually saying I have 256 NICs. I really only have 2 NICs that are one port each. And then inside each one of these, we have virtual functions, and we use virtual functions as protection domains. I'll get into that in a second. Okay, so PFs and VFs are kind of central into how our usNIC function or functionality works. Now, our queue pairs, these send and receive queue pairs that are verbs entities, you know, the send and receive and so on, are inside of our virtual functions. right? So a virtual function has a protection domain that's basically associated with one process, right? So that I can't receive and send on somebody else's behalf, right? I only want to send and receive on the queue pairs that are in my process. I don't want to send and receive on your queue pairs. More to the point, I don't want to, but I don't want to let you do that to me either. So it's a protection domain kind of thing. So our queue pairs are instantiated within the virtual functions. Okay, so let's ground this in a little more reality here for MPI. Let's say I've got a pair of MPI processes, and I've got my PFs, my BFs, and physical ports over there, and I've got the Intel IOMMU. So when an MPI process starts up, it's going to allocate some queue pairs. In particular, in Open MPI, we're going to allocate one queue pair for each physical function for each MPI process, right? So this guy gets a queue pair in this physical function and in that physical function. We do the same thing for the MPI process. All right, now why do we do that? Well, we want the bandwidth multiplier. You know, I want to be able to send large messages and stripe across both ports. Right, so I want to give him basically a mechanism to send out both physical ports and receive from both physical ports. And then the same thing for the other process as well. Okay, and then the Intel IOMMU does the memory management, and I'll get to that in a sec. Actually, I'll get to it right now. So the usNIC verbs driver programs, the usNIC verbs driver, let me take a step back. When you send and receive in an OS bypass kind of way, when MPI sends this, it has to say, hey, take this buffer from RAM and inject it onto the wire as an L2 frame and so on. So how does that happen? Well, the hardware has to actually reach into RAM and get that, right? It has to get that buffer and then send it out. Well, how do you specify where that buffer is? Well, the user space process thinks in terms of virtual memory, right? So it has virtual addresses that all user space things do, right? So he says, hey, I want you to send this buffer, and he gives a virtual address to the VIC. And the VIC says, well, I only know how to speak physical addresses to reach RAM. So I will ask the Intel IOMMU, hey, if I have virtual address A, he tells me what physical address B it is, and then he can reach into RAM and find exactly that buffer. All right. So it is part of the verbs API that it actually programs and deprograms this, what the mappings are of virtual to physical memory. Okay. And this is a big, hefty, fast chip. Super nice. We didn't have to put it on the VIC ourselves. Matter of fact, actually, so this is our second generation VIC. We had an MMU on the first generation VIC, and it was such a pain that we said, heck with it. It's now on the x86 chipset, so why don't we just use that one? So we do. All right, now, the way we advise setting this stuff up here, let's just assume that we're not talking VLANs or any kind of complicated stuff like that. Let's just assume that we've got physical ports. Each physical port has one Linux interface. So like this is ETH4, this is ETH5. And then for each of those, we're going to have one usNIC device. So I've been talking about ETH so far. ETH is the general TCP device, right? usNIC is our OS bypass type. But they have a one-to-one correspondence to each other. All right, this is the way that we've done it. So that since they're really using the same link, it didn't make sense to try and virtualize it and say, oh, I have 6 usNIC devices for that guy. No, we kept it simple, one-to-one. Right? So, and we advise you to have just one physical ETH device for each physical port. You could go a lot more than that if you wanted. You could have physical port or virtual ports, but for the purposes of HPC, you just want one, and then there's one corresponding usNIC device for every ETH device. Okay? All right, so here's my favorite picture again. And if you notice, this is slightly different than the one that I showed in the last presentation, because here's a PCI device. So this is ETH4 and ETH5, which you can't possibly read, so let me blow it up for you. And notice that it's also usNIC 0, usNIC 1, usNIC 2, usNIC 3. Right? So they really are a one-to-one correspondence, and according to Linux, they are the same device. Right? So HWLoc was not written to do anything special here to recognize usNIC. This is all exposed through verbs and PCI and all the normal standard Linuxy mechanisms. And it's just able to read that stuff and say, oh yeah, ETH5 and usNIC1, they're the same actual physical function / physical device. Okay. All right. Now, with that background, let's talk a little bit about how Open MPI itself is architected. All right. Blue up here is the user application, the MPI application. Then inside Open MPI, we have a couple of different layers. And these are a little bit misleading because you're like, wow, that's a lot of deep layers. Isn't MPI supposed to be fast? These are actually really thin. And particularly for the performance critical paths, some of these are really thin. But for architecture purposes, it's easy to think about it this way and abstract it this way so we can keep it straight in our heads. So there's this whole Open MPI layer, and it can actually reach down and touch the operating system. That's why we have the little downward spiral here when necessary. But for sending and receiving, let's just talk about sending and receiving. MPI send, MPI receive. First, it goes through what we call the PML, the point-to-point messaging layer. And then in this particular case, it goes down to what we call the BTL, the byte transfer layer. So this guy, the PML, he's in charge of doing MPI level semantics. So creating MPI requests, doing non-blocking stuff, advancing the requests through all the states, the MPI semantics. This guy here is responsible for talking across the network. He actually knows nothing about MPI semantics at all. So we have lots of different BTL plugins for different types of networks, shared memory, TCP, InfiniBand, usNIC, and so on. And then, of course, you have the operating system and the hardware itself. And what we didn't really show here is that, a lot of these OS bypass ones, the BTL talks directly to the hardware as well. Just can't PowerPoint that very well. All right, so let's talk about how MPI send goes through, right? So if I do an MPI send or an MPI receive, basically it jumps straight to the PML. OB1 is the name of the most common plugin that we use. Yes, it is a Star Wars reference, and yes, it reflects the ability that we can't choose decent names. But then we have these plugin modules, okay? And we treat plugins very much like a C++ class and object, right? So we have a usNIC BTL, but we kind of instantiate that for each of the active devices that are on the server. So during MPI init, we actually kind of investigate the machine and discover what devices are there, and then instantiate BTL modules to match, right? So on the picture, the HWLoc picture that I showed before, I actually have, I had 4 usNIC devices, so I will instantiate 4 usNIC BTLs that match the 2 ports on this VIC and the 2 ports on that VIC. Okay? All right, so let's talk a little bit about the usNIC BTL. Again, it's the byte transfer layer. The BTL does not require or assume any particular protocol. It is totally up to that hardware or that transport or whatever it is hiding behind it. You can do whatever you want. There is no standardized protocol at all. Right? We just give you calls down and say, hey, here's a blob of bytes I need you to send to peer number 38. And however you get that over to peer number 38 is your business. So the way the usNIC BTL works is we use unreliable datagram verbs, right? So verbs is the InfiniBand stack that we're all familiar with. Their little known fact, there's actually 4 different flavors of messaging under verbs. The most common one that you know is called RC, reliable connected. You create a queue pair, which is kind of analogous to a socket. It's to one person, you send things along, it's ordered, it's reliable, and so on. Kind of analogous to TCP, right? There's another flavor of verbs called UD, which is very analogous to UDP. You send MTU size messages. They might go out of order. They might get dropped. It's very much like UDP. So we are using UD in ours, and I'll get into why in a little bit. We handle all the fragmentation and the reassembly. Normally, in all the other BTLs in Open MPI, the PML actually does the fragmentation and reassembly. But we decided it was actually more efficient for us for the PML to say, hey, here's a 1 gigabyte message, go. And we do the fragmentation reassembly ourselves, because it basically means less traversals up and down the stack to say, oh, we finished that one, we finished that one, we finished that one. Now the PML just gives us one big blob, we do our thing, and when all the fragments of that are done, we just send up once and say, hey, that 1 gigabyte blob is done. So it's just more efficient that way. We do handle all the retransmissions and the ACKs in software. and we use a sliding window retransmission scheme. And it's kind of funny because I've been working at Cisco for 7.5 years, and I think I started working on this BTL about a year ago. And I was like, oh yeah, I've been working at Cisco for a long time. I understand networking. Yeah, when you start writing your own window retransmission scheme, you find out how little about networking you really know. They're really complicated stuff. But we have some really smart people working on this, and we have there's a really great optimized algorithm that it's doing. It's basically all the stuff you need out of TCP and all the stuff you don't want that makes it slow. So it's kind of like mini awesome TCP is down in our BTL, and all the stuff that really makes TCP difficult, complicated, and slow, we don't need any of that stuff for MPI, so we didn't include it. Eric. I was wondering when I was going to get this question. I was kind of assuming it would be before I got to this slide. So the question is, why did we do UD instead of RC, right? So why are we doing all this in software rather than offloading it to hardware, right? The answer is very simple. We didn't create this VIC. The VIC is not capable of doing RC. And so UD is what we can do. This generation of VIC, let me rephrase that. Let me rephrase that answer. This generation of VIC is not capable of doing that. The next generation of VIC will be more interesting. And I will give you no dates on when that's going to be available. But like I said, this is our second generation VIC. The second generation VIC was basically more, faster, better compared to the first generation VIC. The third generation VIC, which we have in our labs now, man, that thing is cool. There's some new cool stuff in there that is pretty awesome. And there will be more interesting things coming. But basically, our hardware is limiting us to UD today. All right, last one. Oh, I already talked about this. We direct inject and direct receive L2 Ethernet frames. Okay, so how do we use that in the BTL? Well, in each one, we create 2 endpoints, right? So this is like UDP, right? We just create endpoints and people send to us, right? We create 2 of them. We have a priority one and a data one. The priority one is used for ACKs, for short control messages, sometimes for retransmissions, but basically stuff that goes out and needs to go out quickly so that you don't get deadlock and you don't get live lock and things like that. So we have a priority queue pair. Each one of these has what's also called a completion queue. So when you, for example, when you put something on the send queue, it's an asynchronous activity. You just put it on the send queue and the hardware says, thank you very much. And later, it'll put an event on the completion queue and say, hey, you know that send you gave me? I'm done. All right, so it's all asynchronous. You start something and then you check for its actual completion later. So anytime you do a send or a receive, you just put it on the queue and the send event will complete there or the receive event will complete there. And it's the same for both of these. All right. Now the data queue, we can send up to MTU size data packets. And one of the guys on my team is actually such an incredible wizard that he made the bandwidth to be awesome regardless of whether you do 1,500 size MTUs or 9,000 size MTUs. So you actually don't have to use jumbo frames to still get awesome bandwidth, which was really cool, if you ask me. This is just kind of an interesting note. The queue pairs may or may not be on the same virtual function. We can actually put the queue pairs, they could spread across multiple virtual functions, or they might actually be located in the same virtual function, just depending on how the resources of the VIC were allocated at runtime. It's just kind of a funny quirk that it can end up that way. But basically what happens is that in MPI, I think you're all probably aware that most MPIs spin hard for progress, right? Where latency is king, so we never block, right? We always keep spinning saying, is it done yet? Is it done yet? Is it done yet? Is it done yet? Basically what we're doing is polling these completion queues hard, you know, and they say, nope, nothing's ready. So we'll just ask again, hey, is anything done? So we call that the progress function. And in the progress function, basically we check the priority completion queue first and service anything off of there. And then afterwards, we service the data queues, right? Because by its name, its priority, we need ACKs to go out and retransmissions and things like that. Okay, so let's talk about latency breakdown. So I gave you the latency numbers in the prior talk here. The raw latency with no MPI, no verbs, just minimum sending L2 frames back and forth, none of the verbs API in particular, It's 1.57 micro, and this is half round trip ping pong latency. This is on an Ivy Bridge, a pair of Ivy Bridge servers, by the way. And again, back to back, no switch in between. User space to user space, though. I'm sorry, Sandy Bridge. I said Ivy Bridge, it's Sandy Bridge. If you put MPI on there, we add a little bit more. We're up to about 1.85. So let's break that down a little bit here. So the raw is 1. And these are actually to scale. So 1.57 micro. The Verbs API itself adds about 80 nanoseconds. And then MPI adds about 200 nanoseconds more. So this we are looking at to see if, I mean, that's a third right there, right? So we're looking to see what we can do about that. That's a topic of significant conversation back at Cisco. All right, and this keeps going down as well, not only as processors get faster, but we keep optimizing things in Open MPI. You know, in years past, it was, you know, out there, and it shrunk over time. All right, so let's talk about what we do for ACK optimization. So since we have to do ACKs in software, it's kind of complicated, right? And you have the whole sliding window scheme. Does anybody know what a sliding window scheme? You know what I'm talking about? No, Paul knows. All right, sliding window scheme is basically, how to summarize this quickly. When I set up a connection to a peer, I set up enough buffers to receive 1,000 MTU size messages at once. Right? You have to set up some finite number, right? So when somebody is sending to you, you want to kind of have a gentleman's agreement that says, I will never have more than 1,000 packets in flight to you at once, because it makes no sense, because you don't have the buffers for it, right? But that's not quite true, because even if you've sent 1,010 in flight, I'm still going to have received some by the time, you know, those extra 10 come by, and so I can probably still receive them, right? So I have a window of 1,000, but it's kind of sliding along. As I receive buffers, I can post 10 new ones, and you know, that's why it's called a sliding window, right? So I have 1,000 maximum, but the range of messages that I can receive keeps moving along as I receive new ones and you're sending new ones and so on. So basically, once I receive messages, I send back an ACK to you saying, hey, I received those 7 messages you sent. And therefore, he knows, oh, okay, I can, you know, before I said I could only have 9,993, but he just said he got 7, so we're back up to 1,000, right? So you do a little bit of accounting on both sides to know, am I allowed to send to you or not, right? And you can also be clever about that to know, oh, he said he got number 17, but he never told me he got number 16. So 16 was dropped, and I need to resend 16 to him. So you can do these kinds of knowing what you need to resend and when you need to resend it. But if you're not careful about it, you can do it tremendously inefficiently. So these are some of the optimizations that we did in this area. This is the most obvious way to do it, right? You get a message, you send back an ACK immediately saying, yep, I got number 13 right there. Thank you very much. Not really efficient, because you're basically flooding the network with ACKs, right? And you don't want to. You want to flood the network with data and messages. So you want to do fewer ACKs than this so that you're reducing your overhead, right? So the most obvious thing you can do is, all right, well, let's defer a little bit. I get a couple of messages, and I send an ACK back saying, oh, I've received N plus 2, right? So if this was 5, 6, 7, I just say, oh, I got all the way up to number 7, right? And then he can know I got all 3 of those messages, right? And for our particular hardware and our particular progress function, it actually turns out that anything more than 1 is the biggest win for us. It doesn't matter whether it's 1 or 17. The net average effect is about the same. I'm sorry, 2 or 17. So as long as it's more than 1, that's going to be a big enough win for us, and it's not as much of a win as you would think to do N more than that. But we defer it as long as possible before sending it out, meaning we service all receives, and then we send ACKs when we're done with all the receives for that round. Right? But now, even better than that, you can defer and piggyback, right? So, okay, well, I just serviced all receives. Well, now why don't I go process all the sends that I have to go out? And you know what? I have a send going back to the same guy that I need to send an ACK to. So why don't I set a couple of bits in that message and piggyback the 2 together? I don't need to send a message and an ACK. I can just combine it in one message. And again, decreasing the overhead, decreasing the amount of bytes that are flowing across the network. This is all a good thing. Okay. All right, hardware control. Here's what a normal send looks like. And I used an acronym there without defining it, a bad thing for me. WQ, it's a work queue. Think of it as the send queue. I probably should have just put send queue there. There is an entity called a descriptor. Basically what you do is we send in there saying, oh, here's the buffer, here's the length, here's who it's going to, stuff like that. That's the descriptor, describing where it's going. And one of the elements of that descriptor is a pointer to the actual buffer to send, right? So it's got all the addressing information and then a pointer to the buffer to send it. And basically what we do is we do a PIO send, which is basically a hardware-based send down to the VIC, right? So from user space, we write down the index of this descriptor. Because at the beginning of time, we set up 1,000 descriptors. And so we say, hey, Vic, read descriptor number 17, and that will tell you what to do next. Okay, and so the VIC says, oh, okay, I will go get number 17 from RAM, right? Because they're out in RAM. So he's got to read that. He's got to send something across the PCI bus up to RAM to read number 17. And now he's got the descriptor, and the descriptor now has the buffer address. So he has to do another get across the PCI bus to read the packet from RAM, comes back down to the VIC, and then he can send the whole thing out on the wire. Okay? All right, that is the normal way of doing things. But we also have in our VIC something called a prefetch hint, where you can actually kind of optimize this. Given a certain set of circumstances, which can't always, it's an optimization, so it's not always applicable in every situation, but you can write the index of the descriptor and you can munge in the address of the buffer in one send, right, in one PIO program there. So it's kind of an encoded version of the address. And that allows the VIC to instantiate two reads in parallel. Rather than doing it in serial, he can read the work queue descriptor and read the packet basically immediately after each other without having to wait for it to end. Right? And then he'll get them both back, send them on the wire. The difference for us is about 400 nanoseconds. So it's a pretty giant win. Right? Isn't it kind of amazing that 400 nanoseconds is a pretty giant win? Try and explain that to your kids. All right. So prefetch. This is a hardware feature that's on our VIC that we just took advantage of. It's pretty cool. All right. Other stuff that we discovered. The length of queues are important. This was a huge surprise to me, and I was wondering why we were getting bad performance in early days of this stuff. Our hardware allows us to have a queue depth of 2048. And so as an MPI guy, I'm like, well, yeah, give me all of those. Make queues of maximum depth, because I never know how much stuff is going to be coming in. But then I was seeing lower performance than I expected. I'm like, well, why is that? And the hardware guys are like, does not matter at all how deep your queues are. My hardware will perform exactly the same, whether you have a queue depth of 5 or 2048. And they were insistent on that to me. It took a long time to figure this out. And actually, it wasn't me who figured it out. It was another guy on my team. But he said, you know, if I set the queue depth down to 64, I get significantly better performance. I think it was on, well, yeah, I said that. It's on the order of 200 nanoseconds more. So that's 600 nanoseconds. That's a long time, right? 400 for the prefetch and 200 for this. It's basically because of IOMMU caching. So remember this picture from before? That the user space sends a virtual address to the VIC. The VIC has to send it down to the Intel IOMMU. It gets a blah, 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 right? It's because if we have queues that are this long, well, queues that are shorter, we're really only using this much of the IOMMU rather than this much. And I'm excluding a lot of details here, right? But this is essentially what is happening. It's basically because the IOMMU has a cache of the translations that it's using, and we were thrashing that cache. So if we stay within the cache or closer within it, then the actual lookup on the hardware side happens faster. So basically the compromise we ended up doing is that we basically scale the length of the R cube depending on how many peers there are in the job. All right. Of course, there's an MCA parameter where you could set it explicitly if you wanted to. All right. But that one caught me by surprise a lot. It generated a lot of conversation at Cisco for like 2 weeks. Mm-hmm. I'm not quite sure I understand your question. Mm-hmm. Oh, yes. Now I understand what you're saying. So the question is the performance dependent upon the actual number of messages received, not just the queue depth? Let me think about that. Logically, I'm pretty sure the answer is yes. I think the problem that we ran into was when you run these ping pong benchmarks, you get a lot more than 16 messages. You do fill up the whole 2048 queue, and therefore you're thrashing the cache, the IOMMU cache. All right, so in a real application, probably doesn't matter that much. But unfortunately, everybody runs the point-to-point benchmarks, and we have to make those look good. All right. But that being said, we took a lot of care that 64 was not an arbitrarily chosen number. 64 will still get you full performance in real applications. And the code was structured such that, all right, we're going to reduce this so that we can look good on this one benchmark, but really, benchmarks are only what gets you in the door. Real performance is what keeps you at the customer site, right? So this is actually very well tuned that you will still get very good performance on real applications, even though it's a tweak for a benchmark. Okay. Say that again. So the question is, how did we figure out that this was going on? Is there a performance counter? So this was done by Reese Fawcett, another guy on my team who was a longtime Miracom guy, and we managed to steal him. I'm not going to swear, but I think he did actually query some of the hardware counters to figure this out. And we actually found some bugs in the Intel IOMMU code in the kernel that are still being fixed. So there was a lot of conversations between us and the Intel IOMMU guys to figure this out. Okay. All right. And then something dumb that really had nothing to do with our hardware at all is that you use FastPass whenever possible. And it was surprising how much this had effect. So writing long, gigantic, complicated functions, not a good idea. For things where you can make assumptions about like, oh, I know I have enough queue depth. I know that the rest of the queue is empty, and I can just send this out right now, avoid all the rest of those checks, make a short inline function that does that, and return, otherwise do it, the slower, normal way, had a surprising, noticeable difference. This is coding 101, but when you've been in the business for a long time, sometimes you forget these things, so it's worth mentioning. All right, NUMA effects. So let's talk a little bit more. Again, my favorite picture, ETH4 and usNIC, same here. So this is the same one I showed earlier in the presentation. When MPI processes are running on these cores, only these usNICs will be used for short messages, right? And as far as we can tell, no other BTL and Open MPI is doing it. So we thought we were pretty cool for figuring this out. With short messages, latency is important, right? And so you don't want to have to traverse the QPI between these two NUMA nodes just to get a short message out and say, oh, yeah, aren't we cool that we do multi-device striping and stuff like that? Turns out not so much for short messages. You need to keep them local because a QPI traversal can add as much as a microsecond to your short message latency. And so that is terrible. So long messages, of course, you don't care about the latency, and so therefore we'll use all available devices. All right. Now, back on this picture, though, it's better than that. So let's say that these guys did not exist here, right? In this case, short messages, of course, would have to go up here as well, right? And they would have to pay the penalty for the NUMA. Because let's face it, most HPC installations will only have one NIC, not two, right? I have this because it's a development server. So it basically does a sort. It finds all the VICs in the machine, does a sort by NUMA distance, and then for each process takes the ones that are all equidistant the closest. Did that make sense? Everybody's got a puzzled look on their face. So it finds all the VICs, and it sorts them by distance, right? So the first one on the list will be the closest, and that's of distance x, right? So then we take all devices that are distance x. So in this case, you would get both. Right? You don't want to take just the first one because there could be another one that's the same NUMA distance. So we thought that was a pretty cool little optimization. And it makes a difference. That is a great question. The question is, how short is short? So we have an adjusting slide for that. Let's see, what is it? When there's only one usNIC device, it's like 120K. And when you have more than one, it's like 58K. And it's really weird, but it's basically, when you do multi-device like this, it means there are more places that MPI has to check for completions. And so therefore you are by definition adding latency, right? And so normally when we do point-to-point benchmarks, we only run with one, right? And let's be honest, the way all HPC, well, many HPC installations are, you buy one NIC and you have one port active, right? But when you add more, it's a complicated calculus of, I have more bandwidth, but I'm checking more places, so what's the overall latency? And so we did that, that division of one versus more than one because it just works out better that way. That was actually determined empirically. That when I have multiple things, when I go above a smaller number, I want to start splitting out the bandwidth versus, oh, I only have one guy, so let's take all the short message paths for up to a larger number. That was a very coarse-grained explanation for a complex phenomenon. I hope that was enough. Okay? Paul's laughing at me over there, by the way. Okay. Other bit about this, it's all open source. Everything above the firmware, that is. The firmware, of course, is closed source. But it's really cool to work in a giant company and be able to represent them in the open source community. And say, yeah, all the cool things. So all that stuff, that's all in the code. You can all go look at that. You can steal all of our sliding window tricks and the retransmission tricks. All that stuff is upstream in Open MPI. You are free to use it. It's BSD licensed, all that good stuff. That's just really cool. I'm actually fairly proud to work at a company that not only allows this, but encourages this. So I like putting this open source slide up here because it's just a cool thing. There are multiple parts of it. Right, so there's Open MPI. So this requires a little bit of an explanation. In the 1.6 series, so I think almost all of you were in the last talk, this is the stable series of Open MPI. They do not accept new features upstream. usNIC is a new feature. So therefore, they would not take usNIC in the 1.6 series. So we basically are distributing Cisco Open MPI, which is exactly 1.6.5 plus our BTL. But we got the usNIC BTL upstream in 1.7.3, which is publicly available in the subversion. It's all out there. Right. Then there are two other parts of it. There's the libIB verbs plugin, which is the user space stuff, and then the verbs kernel module, which is the driver that talks to our VIC hardware. All that stuff is open source. All right, so let's look at a couple of performance graphs. This is all the details so that it's reproducible. These are on Sandy Bridge machines, and with that kind of memory, this particular VIC, this particular the Cisco, the Nexus switch that I mentioned before, blah, 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 blah. Okay. This is NetPipe. NetPipe is a half-round trip ping-pong benchmark. The blue line is the latency. The green neon there is the throughput. So we start off at 2.05 microseconds for latency for small messages, and we go up to something larger than that. I don't know what the number is offhand. And then the bandwidth traverses nicely up to, and again, this is on one interface, right? Not four. So otherwise, it would go much closer to 40 gig rather than close to 10 gig. All right. So we ramp up nicely to the max bandwidth. MPI benchmark, so the IMBs, this is the ping pong and ping ping. So ping pong is pretty much exactly the same thing as NetPipe. You send a message, he receives it, and then sends it back. You do that a bazillion times, you divide by a bazillion, then you divide by 2, So you get an average half round trip time. It's pretty much exactly what ping pong is too. Ping ping is you both send at the same time and receive at the same time. Do that a bazillion times, divide by a bazillion, divide by half. All right, so ping has simultaneous traffic. Ping pong only has one message on the wire at a time. Okay, we didn't make these up. That's what's there. But let's see. So green is ping pong, the one message. Blue is ping ping, the two simultaneous messages. And again, starts off at about 2.05 when you have the simultaneous stuff happening. It's a little more completions you got to check for at the same time. So we add about 50 nanos there. What's that? I don't think that, no, they do not. It is too, so you have to send and receive into a different buffer. Since you have a send and receive going on concurrently, it has to be a different buffer. Okay. I'm sorry, I didn't repeat it for the question is, in ping pong, do they use the same buffer and over again, or is it a new buffer every time? I honestly forget. I think in the IMB, it's the same buffer over and over again, but I'm not going to swear to it. But doing that allows you to avoid caching effects, and you're testing more networky things. That's why Eric was asking. All right, send, receive, and exchange. Basically, this is more bidirectional types of testing. So send, receive it's a little different than ping pong. I'm sorry, ping ping. You do have messages going on simultaneously, but it's an MPI primitive. It's one function, send, receive. You give both a send buffer and a receive buffer. And so it's really just checking how well your MPI handles that. Exchange is a little more complicated than that. But basically, everything ramps up actually kind of nicely. That, we're at 2.11, which is right in the right ballpark, and 2.58 for exchange, and so on. And all the bandwidth ramps up nicely. All right. LinPack is one that everybody talks about. We all do the standard disclaimer of LinPack. LinPack is one particular benchmark. It's not the end-all, be-all. But we actually are pleased with how we did on that. So this is up to 512 cores of Sandy Bridge. And we got up to an efficiency of 89.69%. And that we were actually very pleased with. So we got up to 422 gigaflops is the theoretical max, right? Yes, and we got 340. I'm sorry, that's a single node. And then across that, we got 9773. So this is the theoretical max for a single machine of 16 cores. All right, so the efficiency all worked out to just under 90%. It's kind of cool. Okay, that is all I have. You got to finish with some performance slides. I hope I didn't go too deep there, but I just wanted to show that basically, and I want to reemphasize this point, this is a time-tested and true NIC. This is not something that was invented for HPC. The reason I'm pointing that out is because it has been in use in commercial data centers for a year and a half. And so it's actually a pretty solid, robust NIC in itself. We're just taking advantage of some of its functionality with new firmware, new Linux drivers, and we can actually get pretty awesome performance in the HPC context. Next generation VIC and the one that's going on beyond that have even more cooler features that they actually asked our input on. What do you need for HPC? What do you need for MPI? There's some cool stuff that's going to be coming. So since we actually had some input into the design of next gen hardware. So that is all I got. Any further questions? Eric. I'm sorry? The question is, does this work under virtualization? The answer is no. We get this question a lot, particularly because our VIC is a virtualized NIC. And like, oh, well, why can't you just bypass both the hypervisor and the OS? We call that double bypass. My boss is a much better expert on this than I am. There are several pieces missing from Linux to allow that. So it's not just a matter of writing your own driver and doing the double bypass. There's things that the Linux itself needs to have that nobody is working on. And so that we're not super excited about trying to do that ourselves. Much more promising is the idea of containers that's in the recent 3.x kernels. That is actually a whole lot easier to do you get the same end effect of virtualization, that you could do multi-tenant stuff and clear separation of data and traffic and process space and file space and all these kinds of things, but you don't have to deal with a hypervisor, and therefore you can do OS bypass but still have the separation that you want from virtualization. So that is something that a lot of people are talking about, not just Cisco. So I have nothing definite to say in that arena other than that looks kind of interesting. Yes, sir. Mm-hmm.
And how is the simplicity, are they using hardware buffers or different hardware buffers? And how the performance for the VNIC is going to be affected by the traffic on the Ethernet?
Great question. So the question is, in a converged environment where I'm using both the ETH device and the usNIC device, what happens, right? They are using the same network link, right? So if you've got a 10 gig link or a 40 gig link, one way or another, you're dividing up the bandwidth, right? You can be actually very clever about it and assign different qualities of service to the ETH device and the usNIC device. Even put them on different VLANs if you wanted to, for example. So you can regulate down the ETH traffic to, X% and give the rest of it to MPI, or give the rest of it to the usNIC device and stuff like that. Second part of the question you asked was, are they the same hardware buffers? And the answer is no, because they will have basically a different virtual function. And our VIC has enough hardware buffers and other resources to handle having up to 256 physical functions. And so it's got enough beef to handle basically parallel streams of traffic. On a 10 gig link, you'll probably run out of bandwidth before you run out of buffers. All right, on a 40 gig link, there's enough to feed it all. I'm not allowed to say when the 40 gig form factor is going to be released, but we have them in the lab and we've done this kind of testing and it actually works out pretty well. So you can do fairly complex stuff to set the, make sure that, oh, when I do an SCP over the ETH link and I'm doing a big honking file transfer, I still limit it down so that MPI gets the bulk of the bandwidth. Did that answer your question? Okay. Paul.
Same question, but add FCOE to the mix. I assume what I do here is this VIC is capable of fiber channel Ethernet.
Yep.
As well. Same rules as far as quality of service, etc. I can make sure that the fiber channel rate stuff doesn't starve my MPI for
yeah, so the question is, Paul's asking about the VIC is also capable of fiber channel over Ethernet, FCOE, storage protocol kinds of things. Does my same answer apply when we do FCOE as well? The answer is theoretically yes. I have not personally tested that. We have not personally tested that because we don't really do much FCOE. But yes, all those personalities coexist in the VIC. I'm pretty sure that you can do all the same quality of service stuff with FCOE that you can with normal Ethernet stuff. So don't take that as gospel writ, but take it as I'm pretty sure that is possible. Right? So you could limit your fiber channel traffic to this much, your SSH traffic to this much, and your MPI traffic to effectively your MPI traffic to that much. So fun little fact there. The drivers for all these things, so we've got usNIC driver down in the kernel. We've got eNIC for the Ethernet NIC and fNIC for the fiber channel. Those are all the Linux driver names. Yeah.
So these look like special NICs, right? So compared to standard, how much price
so the question is, this is a very specialized NIC. What's the cost difference between, say, a gigabit Ethernet NIC? That's hard to say because this is a 10 gig and then there's going to be a 40 gig form factor. You can buy a 1 gig piece of crap NIC for $10. So, effectively it's a giant price difference, right? But they are quite comparable. I'm not on the sales side, so I don't know. There's the list price and then there's, what do you actually buy it for? I'm told that the VIC is actually very price compatible with, or price comparable to most other 10 gig NICs. I'm told it's a reasonable value. And the Cisco account manager says, yes, buy 20. Yes.
I'm not sure if I missed that. So is that the basic support after 80
Correct.
So is that even is that for the current generation ended unit or for the future 40
So yeah, let me clarify that. The current generation VIC has an 80 gig ASIC, but it only has two 10 gigs out, right? So it's not the next generation of the VIC that will be 2 times 40. It's just another form factor of the same VIC, right? So it's the same 80 gig thing. We're just putting different PHYs and whatever. I'm not a hardware guy. I mean, to me, it's just slapping on a new PHY and calling it done. But apparently, it's a little more complicated than that. They're putting new PHYs on there for 40 gig, but it's the same old ASIC. So it's really kind of like, you know, Rev 2 of the same generation. And that is coming very, very soon. Whereas the third generation of the VIC, which has all kinds of new stuff on it that I can't talk about, is coming in the indeterminate future. Did that answer your question? Yeah. I would say you're probably never getting XRC. So the question is, for the next generation of VIC, can I comment on when we're going to get XRC? XRC is an InfiniBand thing. That has nothing to do with Ethernet. Right, so XRC is an extension to InfiniBand invented by Mellanox. Right, so it's not. Yeah. Today we only do UD.
Right.
That is all I can say. I've gotten in trouble before, and I'm not going to get in trouble today. I think you can infer what I'm saying, but I am saying today we can only do UD. Thank you very much for your time. Appreciate it.